Hey there, chemists. In this lesson, we're going to look at different chair conformations. Remember, that's the more stable form of a six-membered ring as opposed to the boat conformation. And we learned at the end of our last lesson that there's a difference between what's called an axial substituent and an equatorial substituent. Now, on the screen in front of you, you have a static chair cyclohexane representation. And they drew a green plane to show somewhat of a plane for the ring itself. Even though a chair cyclohexane ring is not flat, we can still talk about the things coming off of the ring as being slightly above the ring or slightly below the ring, given this particular perspective. Now, what I want you to do is focus on the hydrogen that's all the way to the right in this picture, because we're about to animate it and have it turn into a different chair conformation. Let's confirm two things at our starting point. The one all the way to the right is currently slightly above the ring. It's sticking above that green plane. And I can tell that because I can also see the other hydrogen on the same carbon that's pointing straight down and axial. So I have, if we're all looking at the same one, all the way to the right, I have an up equatorial hydrogen right now. And I just want you to focus on that. And what I'm going to do is contort this a little bit differently. And I just want you to follow what happens to that one hydrogen. Here we go. Okay. Twisting around some bonds, puckering around. It was a chair. And now let me pause it. And what we have here is a different chair conformation. This is the same molecule. It's a different conformational isomer. It's just rotated around single bonds. We didn't break any bonds. This is not a constitutional isomer. We've just twisted it in such a way that it's a different chair conformer. Now, if you were following that one hydrogen, hopefully you've noticed it's still above the plane. It's still sticking above the green plane, even easier to see now. But it used to be equatorial, and now it's axial. So when we underwent this conformational change, equatorial became axial. I want you to watch again and pay attention to that same H, just in case you missed it, and confirm where we are right now. It's currently above the ring and in an axial position. And now let's twist it back. Everything's rotating. And now we're back to a different chair, actually the original one that we started with, and that same hydrogen still above the ring. It's never not been above the ring, but it's back to an equatorial spot. And this is what all six-membered rings have the ability to do. They can interconvert between two different chair conformations. And when that happens, whatever is equatorial becomes axial, and vice versa. Whatever's axial becomes equatorial. But the relative placement of where they are on the ring, if it's slightly above the ring, pointing above the ring, or pointing below the ring, that stays the same. So what we're going to do is look at different ways to draw these things and talk about the axial and equatorial differences and what happens when they're above and below the ring, and specifically when we have multiple substituents. So first, let's just practice interpreting a chair and making sure we understand what to do with multiple substituents. So here's a cyclohexane with 3 methyls on it, and I want to draw a flat hexagon structure for this. The first thing I'm going to do is pick a place to give myself a perspective, and I'll choose that. Floating above the ring, looking down at it. What would it look like? Well, I have my flat hexagon, and from that perspective, which is arbitrary, I need to pick some position to be one of the spots where the methyl is. So I'm going to say that this carbon is this one in the upper right. So I'm actually going to highlight that right there just to keep my frame of reference. Now, where is that methyl? Is it coming toward me with a bold line, or is it going away from me with a dashed line? It might be hard to tell at first, but look at what else is on that carbon. There's a hydrogen, and it's currently down and axial because the methyl is slightly above the ring and equatorial. So that methyl I'm going to draw with a bold line. It is more toward me than away from me. So I give it a bold line. What about this methyl? Where is that particular methyl? Well, that's on this carbon that I'll label with that color. And relative to the first one, that would be down there. It was arbitrary where I started, but now everything has to be correct relative to that starting point. This methyl is slightly away from me, so I'm going to draw it with a dashed line. How do I know that? Well, it's currently in a chair down and axial, and there is an up equatorial hydrogen. Remember, we don't draw the hydrogens, but we know that they are there. There's one more to draw, and it's this methyl. and that would be on that carbon right there, one more around the ring. It's currently away from me because there is an up axial hydrogen, so I'm going to draw it away from me. And that's an accurate, flat hexagon version of this particular chair conformation. Let's just highlight in our original one what's axial and what's equatorial to make sure everyone understands that. This first methyl was equatorial, this second one was axial, and this third one was equatorial. And I'm going to call them up and down to mean sort of above the ring or below the ring relative to some imaginary plane that doesn't really exist for this particular chair, but analogous to that animation we saw. This first methyl is equatorial and ever so slightly up. The second methyl is axial and clearly straight down. The third methyl is equatorial and ever so slightly down. It's more down than up. So I'm going to give each one this designation of equatorial or axial and up and down. Why am I doing this? Well, I'm trying to show that just because you're equatorial has nothing to do with which direction you're pointing at. We have equatorial down positions and we have equatorial up positions. Likewise, we have axial down positions and we have axial up positions. And up and down is all relative, but I'm using this as a static chair, and that's how we'll talk about it here. Now, we saw that these things can undergo a ring flip. That's what we call it when it goes from one chair conformation to another chair conformation. And when we do this, everything that was axial becomes equatorial, and everything that's equatorial becomes axial, but up stays up and down stays down. Now, typically when you draw a ring flip, you don't have to do this, but however you originally drew your chair, whatever direction it was slanted in, we usually draw it slanted in the other direction. You don't have to do this, but I'm a little partial to this. So this first one is slanted a little bit to the right, so I'm gonna draw the new chair slanted a little bit to the left. Remember, a chair is 3 sets of parallel lines connected like so. It doesn't have to be perfect. Notice none of the chairs in the ring are parallel to the edge of my piece of paper. Those lines are reserved for axial substituents. Axial substituents are parallel to each other and parallel to the edge of your page. The bonds in the chair and the bonds that make up equatorial bonds are not parallel to any of the right angles on your piece of paper. Now let's pick a carbon to be this starting point with an isopropyl group. I'll make it this one down here. I currently have an isopropyl that's equatorial and down. So it's going to become down, but now axial, IPR. And I'll work my way around the ring. If I go counterclockwise, like so, I get to this methyl 2 carbons away. So that brings me to, if I call this number 1, 2, 3, that's on 1, 2, 3 on that position. It was up and axial, now it's going to be up and equatorial. And that's a good way to show an equatorial bond. Let me zoom in for a second. The equatorial bonds are a little harder to see, I think, but they're parallel to other parts of the ring. That's how you know how it's equatorial. The axials are parallel to the edge of your paper, as opposed to being parallel to other parts of the ring. There's one more bond to throw in, one more group, the hydroxyl group. It was right next to the carbon with the methyl on it, so that's here in my chair. It's currently up, and it's going to become axial. Let me actually clean up how I draw this methyl group just to make it a little roomier. There's our OH. So we started with a down equatorial isopropyl, and we ended up with a down axial isopropyl. Likewise, we started with an up axial methyl group, and we have an up equatorial methyl group. And this was up and equatorial, and this hydroxyl is now up and axial. And that's a ring flip. Everything that's up stays up, everything that's equatorial becomes axial, and vice versa. Lastly, which one do you think is better? Even though both are possible, the whole point of this unit is to talk about the more stable conformation that a molecule can exist in. And between the 2 chair conformers, the bigger groups want to be equatorial. Equatorial is preferred. So we have 1 axial methyl, 2 equatorial groups, as opposed to 2 axial groups and only 1 equatorial group. So clearly, the one that we started with is more stable. And that's simply because there's more groups that are equatorial. More equatorial groups. But sometimes the size of the group can actually overpower the number of how many of them are in an axial or equatorial spot. For example, isopropyl is pretty large. It takes up a lot of steric space. So looking at this right away makes me think, oh, the isopropyl really wants to be equatorial. Probably depends on how many other groups there are and what the sizes of them, but luckily it is synergistic with the fact that we have 2 equatorials and 1 axial methyl in this one as opposed to the other one. Now it's an equilibrium mixture. That's why this is a double arrow, not a resonance arrow. That means an equilibrium between the two. So it is interconverting between one and the other, but it probably spends most of its time in that conformation. Okay, so let's practice this with a couple of other conformations. For each one of these, we're going to show 2 chair conformers and try to identify which one we think is more stable. So I'll start by drawing an arbitrary chair. This one is slanted a little bit to the right. And now I have 2 methyls. One has to be above the ring and one below the ring. And I'm going to pick a place to start. I'll say that this carbon at the top of my ring is that carbon right there in the upper right. This is arbitrary where you start, but now everything has to be put in accurately relative to how I drew my chair. This is an up position. It's toward me, so I'm going to call it up and make it above the ring. So what's up at that particular carbon? Is it axial or equatorial? Let me show you what I mean. Is it correct to draw a bond straight up and axial like that? Or bend it a little bit up and make it equatorial? Well, remember, the axial bonds are indicated by these corners as if they're arrowheads, and that looks like an arrowhead pointing up. So at that position, you have an up axial bond. So that's that methyl right there. And then I have to go around the ring 2 carbons, go around the ring 2 carbons, and I get to this spot, and it has to be down. So I get to this position, and I need a down methyl, meaning below the ring. So do I show it straight down and end up with an axial bond, or down and at an angle, or maybe down and at an angle like that to make it equatorial? Which one is correct? Well, at this carbon, down is equatorial, the way I've drawn the chair. How do I know that? Look at the corner. It's an arrowhead. It's pointing up axial. So I have a down methyl. And I try to make it a little bit parallel to those other bonds in the ring. Now I ring flip it. Draw an equilibrium arrow, slant my chair in the other direction. So I'll take this carbon and I'll make it over here. That way my up axial methyl becomes up and equatorial. And then this carbon will, relative to that, be over here. My down equatorial methyl is now going to be down and axial. And lastly, which of these is preferred? Well, we have 1 axial methyl and 1 equatorial methyl in each one, so they're actually equal in energy. Neither of them is more stable than the other. Let's try another one right below that. Okay, so again, we start with a chair, arbitrarily make it slanted a little bit to the right. I pick a place to start. I'll say that this carbon is this carbon. I need a methyl that's above the ring, toward me, up. So up at this carbon is axial, so I put a methyl straight up and axial. Working my way around the ring counterclockwise gets me to this carbon right here, where the tert-butyl is. It's also above the ring. It's pointing in the same direction as the methyl, so it's also up relative to this ring, and up at this carbon is also axial. Now I draw a ring flip for this. I like to draw them where you slant it in the other direction. That carbon right there, I'll say is that carbon there. That way my up axial methyl becomes up equatorial. And then relative to that, I work my way around the ring counterclockwise. I get to this carbon right there, so that up equatorial becomes up equatorial like that. And then which one's better? Well, we have both groups equatorial in the second one that I drew, so that's the more stable conformer. And by the way, the Turt beetle group is a beast. That is huge. So it is almost always going to adopt an equatorial conformation, almost independent of how many other groups you have that are in axial spots as a result. There's obviously some exceptions to that, and we'll see some really interesting ones with heterocycles. But for now, you see Turt beetle, it's going to be pretty predominantly in an equatorial position. Let's try a few more. Here we have a trimethyl cyclohexane. Start with an arbitrary chair. We have 3 methyls on alternating carbons, 1, 2, 3, all pointing in the same direction, all above the ring. And I can do that very quickly. 1, 2, 3. Up, axial, up, axial, up, axial. Let's ring flip it. That would give me 3 that are all equatorial. Up, equatorial. Up, equatorial. Up, equatorial. Equatorial is for sure preferred. Next one. They give us a name, trans, meaning in opposite directions. 1-ethyl, 3-methyl cyclohexane. So I'm going to just draw the chair first. And fill in what it is based on the name as I go. 1-ethyl. I'll say that ethyl is right here, so I have to have an ethyl on that carbon. I'll make it up an axial. I don't know that from the name, it doesn't really matter. And then trans means on carbons 1 and 3, they're pointing in opposite directions. So on carbon 3, I have a methyl, and it's got to be pointing down below the ring. So if this is carbon 1, this could be carbon 3, far enough away from it. That has to be a down methyl, that would be down an equatorial. Let's ring flip it. Say that carbon becomes that carbon. My up axial ethyl became up equatorial ethyl, and then relative to that I have a methyl right there. My down equatorial methyl is going to become a down axial methyl. Okay, so there's 4 more. I'd like you to hit pause and try the remaining 4, see how well you do, come back and check. Okay, let's see how we did. So for E, we have a dimethyl cyclohexane on opposite ends of the ring. I have a methyl on carbon 1, another methyl on carbon 4. One of them has to be axial, the other one has to be equatorial in order for them to be on those relative spots of the ring and both pointing above the ring. If I ring flip it, hopefully you can already tell, you're going to get an up equatorial and an up axial. These are equal in energy. Neither one is better than the other. F, this is glucose. This is a fun one. This is a heterocycle, meaning it's not all carbons. And one way that you can draw this molecule looks like this. I did that very quickly, but let's check and make sure that it makes sense. Here we have our oxygen as a frame of reference, so relative to that, I'm going to work my way around the ring clockwise, and I'll work my way around the ring clockwise and make sure everything is in the right relative spot. So I can even number them to help me keep track. Let's call this carbon 1, 2, 3, 4, and 5. Then we have 1, 2, 3, 4, and 5. I have an up hydroxyl. There's my up hydroxyl. Then down, down, up, up, down, down, up, and up. So everything fit, and luckily this is an easy way to memorize glucose. It's the chair conformer where everything is equatorial. There is a ring flip of this, and I'm going to start with drawing it slanted in the other direction. And the ring flip will have everything axial, which hopefully you can already tell is a much less stable conformer, so all equatorial is preferred. Next one, much simpler, only one substituent, one isopropyl group. It's dashed, but it doesn't really matter. I could turn this molecule upside down, so I'll have it right there, pointing below the ring. Ring flip it. And now it's equatorial and still below the ring. You could certainly draw any of these upside down, right? That's what is sometimes the most challenging thing about organic chemistry, is being able to recognize when you're looking at the same molecule just from a different perspective. There's infinite perspectives that we have with these molecules. Our job is to make sure we're not accidentally changing the molecular architecture when we draw it differently. Last one, this is a cis conformer of a T-butyl ethyl cyclohexane on carbons 1 and 3. Cis means they're pointing in the same direction. So I'll draw a chair. On carbons 1 and 3, let's say that's 1 and that's 3. I have to have a tert-butyl on 1 and an ethyl on 3, and they're pointing the same direction. I'll make them both above the ring. A little arbitrary, but above would be up axial there, and also up axial there. There's my, ethyl, not methyl, ET. And then if I ring flip this, you would get an up equatorial tert-butyl and an up equatorial ethyl. All equatorial, definitely more stable. Okay, so in summary, chairs can exist as two different conformers. Oh, we never actually said which one was better down here. In D, that was the one where the bulkier, slightly bulkier ethyl group prefers to be in an equatorial position. There, that's more of the summary. Likewise with this, the bulkier isopropyl group prefers to be equatorial, but we almost always have to consider both. Sometimes they're equal in energy, and sometimes they're not. Sometimes the chairs are very different.